Alright, decided to make another video here about navigating celestially in SH5. So I've been asked by a friend of mine, Hunter, to do a demonstration of how I do a full day of celestial in the game. So for those of you who have not investigated doing this, basically if you download the latest version of TWOS and activate it, you'll get a few options for real navigation and then also a real navigation sextant. So if you do want to pursue this route, I would look to Alpharets on subsim.com, also his YouTube channel. He's done tremendous work to make this actually possible in SH5, correcting all of the star and moon and sun data, so that when you actually do the measurements with the sextant in the game, you get real-world results when you actually reduce the sites, go about actually doing the calculations and putting it on the chart. And so credit goes to him. I helped him in a very small way with a couple of things, but by all means, Alvarez is the man of the hour in terms of making this happen in the game. So that said, I would check him out, check his Discord out, check him out on Subsim, and then also check out and I would subscribe to his YouTube channel, because his YouTube channel is chock full of tutorials that show in more detail some of the aspects that I'm going to demonstrate here. So for this, the approach I'm going to take is I am going to do a morning twilight star sight using 2 stars, and then what I'll do also is do a running fix using the sun. Now, it is November, and I am in somewhat of a northern latitude, and so we might have an issue with the sun being a little on the low side. That tends to throw off your altitude measurements with the sextant a little bit with the sun because of refraction, and so I actually we may not be spot on, but just for purposes of demonstration, I'll demonstrate the running fix as well. If I can't get a running fix with the sun, and a running fix is basically you take a sun line somewhere in the morning, right, to get a line of position, and then you take another site, get another sun line somewhere around local noon, and then you advance that morning line up to the second line, and then where those lines cross is your position. It's not perfect because, again, it's based on your dead reckoning, but it's an option that's out there. So I'll typically just do a morning star sight, which provides a real fix to based on 2 stars, 2 lines of position. It's analogous to basically passing by a coastline and seeing 2 different lighthouses and getting a bearing to each where those bearings cross is your position. With the sun, it's like you've got one lighthouse and you take a bearing on it and then wait 2 to 3 hours. You take another bearing when the bearing is sufficiently changed, and then you advance the first bearing to the second bearing. Where those cross is your running fix. Okay, a star sight in the morning and then a running fix during the day. Typically call it good at that. If I can't get a running fix with the sun during the day, I'll do another star sight at night, just so that I've got basically all told 2 celestial fixes per day, and I'll call it good. In the real world, with a navigator, you might do much more work than that. Might do a morning star sight, do some running fixes during the day with the sun, and then do an evening star sight, maybe using 3, 4, 5, or 6 stars or whatever. You're gonna get burned out real fast if you try to do that full-blown approach in the game. So I just call it good with a morning star sight and then a running fix with the sun. Okay, so where we currently sit now is I have got my some marks on the map here. I typically, for any celestial fixes, I typically when I make my mark, I put a compass circle around it, and then these are my dead reckoning positions here, and there's another fix. So this would have been, it's 0016 on the morning of November 3rd. I'm on my way back to my target, so to speak, is Helgoland. I want to make it back there, and then to go back to Wilhelmshaven after that. So, but I'm en route now. I've expended all my torpedoes. I'm back. I'm heading back. And so what I want to do is get a fix at morning twilight. So that's going to be in about 6 or 7 hours or so, and then do a running fix after that. But you can see this would have been yesterday morning's fix, right? And then I would have dead reckoned usually every 4 hours, midnight, 04, 08, 12, 16, 20, and then midnight again. I do my DRs every 4 hours. And then this would have been last night's star fix. I did not get a sun's fix because the sun is so low, given the latitude and given the time of year. Okay, so that being said, I'm trying to steer a course of 133. The weather is atrocious right now, and so because of that, the boat is yawing, and I need to keep an eye on the compass to make sure that I'm not getting thrown off course too badly. Okay, so you can see. So if I look at, I've got the compass mod installed, so it's just a function of making adjustments using the rudder every so often. Okay, to get back on course, roughly on course anyway. Okay, so that's that. All right, so my first step, say it's a new day. I need to figure out when nautical twilight is going to be for the morning. Okay, so Alfred's actually has a table for that, and we can show how to calculate that here. So that would be here. If you go into his drive, it's the file called SH5 nautical twilight, 39 through 45 here, northern latitudes. So in my case, I've got it's November 3rd. My latitude is about 57 degrees north. So I look here, and I can see it's going to be between 0633 and 0628. Okay. Alfred in his videos explains the whole dynamic of zone time as it relates to SH5. So if you depart from these ports here, the GMT that shows in your game is actually 1 hour ahead of the GMT for celestial purposes in the game. Okay, or I should say just GMT in general. Okay, so that's why. So these tabulated amounts are actually real GMT in the game. So this is why it says add an hour. So in this case, we see 633, 628. So call it 0630. Okay, so on our clock in GMT in the game, that's going to be 0730. All right. So that's at Greenwich. Okay, so I need to adjust that for my longitude. Now I know that my longitude at about the time of when I take that site is going to be, I can figure that out real quick here. So that's about call it 7 hours away. Okay, so 7 hours away. So if I do the math, I'm traveling 8 knots. 7 hours. 7 times 6 is what, 420. So I call it 7.5 hours away. So 7 hours is 420 minutes plus 30 is 450 minutes. So I use the nomograph and I say, okay, I'll drop the 0 and just use 45, just like this. Okay, so 45 minutes. And I look in the middle there, and that's going to be about 105. So that's showing about 10.5. Since I dropped the 0, move the decimal over again, that's going to give me 105 kilometers. What I could have, so I just dropping the 0 makes it easier to use the nomograph. Okay, so 105. So that's from here. That's my last position as of midnight. 105 kilometers is going to put me right about here. If I look here, it's going to be about 4.6, about 4 degrees, about 36 minutes. Okay, so if you take a calculator and you do 4.6 divided by 15, because there's because 360 divided by 15 is 24, so every hour corresponds to 15 degrees, 360 degrees, 24 hours. So if I take 4.6 divided by 15, and then I take, and then I have to actually subtract that from the amount in this table because I'm east of Greenwich. Okay, if you were west of Greenwich, you would add that adjustment. But since I'm east of Greenwich, so what is that times 60? So that's about 18 minutes. All right, and again, to do that, another way you could do it is you could say 4.6 divided by 360 times 24. Okay, that's going to give me 0.3 hours times 60 is 18 minutes. Okay, so what I do is I subtract 18 minutes from 6:30, which is going to be 6:12. I add an hour because this is an hour, because our clock is an hour ahead, essentially. And so I get 7:12 is what I need to set my alarm for eventually. Okay, so that's how to figure out nautical twilight. And again, that's actually when nautical twilight ends. So we don't want to do it right on that time. We don't want to do it at 7:12. We want to set our clock for maybe like 7. Okay, so we'll remember to do that. The first thing I'm going to do, though, because I get a DR position every 4 hours, I've got my alarm set for 04. Here was my last one at midnight. So at 04, I'm going to make another mark.
Ja, laufen auf beiden Dieselmaschinen.
All right, so my course is good. Below, the course is good. So then I can TC. I usually just TC 256 max. Just it's a good manageable speed. And then I'm going to TC up to 0400, and then that's just going to be a DR position. Keep an eye on the course. Make sure if it's 133, it doesn't need to be spot on. But if it's, if this indicator here is showing the course that you want to steer, then you're good. You don't need to get super crazy about getting it right on the notch. So another hour will go by, and then we'll make a mark for our DR. So at 8 knots, we can use this at 8 knots in 4 hours, which is 240 minutes. Drop the 0, use 24, and that's going to be about like.
Laufen auf beiden Dieselmaschinen. Fahrt bei dem Wetter 1, 4. Knoten.
It's going to be about like 59, because it says 5.9 kilometers, so again, move the decimal over, 59. So I do my DR, 59. The other thing I like to do is I don't go when I do my DR, I don't go below this zoom, so I can see the entire amount, the entire grid, latitude, longitude grid, so I can make my measurements quickly. I don't like to go in and out and all that stuff. I like to sort of keep it like this. Adds a little inaccuracy, and then it also just makes it so that you don't have to zoom in and out all the time. Alright, so 59, so that's going to be my 0400, and since it's 0400, I'm going to go in and make an entry just to reserve it. Oops, there we go. And then I got some cleanup to do here. All this garbage that gets put into this is fine. No, it goes. There we go. Okay. That'll be reserved for my DR position when I figure it out. Alright, so at 0400, we are at. So the lat long grid is delineated in 120 kilometers, right? So since the SH5 world is flat, every degree of latitude and every degree of longitude is always going to be 120 kilometers, excuse me. 120 divided by 2 is 60. In the real world, every minute at the equator, every degree of longitude is 60 arc minutes, and regardless of where you are on the Earth, in simplistic terms, every degree of latitude equals 60 arc minutes. But obviously, since in the real world, since the lines of longitude converge the closer they go to the poles, that distance between those longitude lines gets shorter the further north or further south you go. That's not the case in SH5. It's completely flat. It's just every one of these is a square. So, and it happens to be 120 kilometers. Now, that's not perfect because the conversion isn't exactly 2. It's 1.852. But for purposes of figuring out lat long, you just divide by 2 or multiply by 2. So you start with a kilometer figure that you're measuring with the map tools. You just divide that by 2, round it off to the nearest minute, and you're good. So let's see how we do that here. Okay, so this is the mark we made here. So I'm going to figure out where I am here based on DR. That is 48.7. We round it down to 48, so we can divide it by 2, and then we figure out what the longitude is here. Right. So here we go. We got enough information now. So that's 57. So we can say that's going to be, and this is the notation I use, 57. I just use a period. Whoops, period. And that's going to be, because this here is 48.7, I round it down to 48, and I divide by 2 is 24. So 24 minutes north space, and then 4 degrees from here to here is 38. Round it down to 38, so I can divide by 2, and that's going to be 19. So that's 419 east. 419 east. Alright, so that's my entry. So every 4 hours I'll do that, log my position, and then I will also have the navigator get the weather, so that we can make a weather notation in here as well. Okay, so that's what we do every 4 hours, regardless of whether we get a fix or whatnot. We do that every 4 hours, just as was historically done in the KTBs, just to get a notation a dead reckoning notation every 4 hours. Okay, and weather and other pertinent information. All right, so that's that. So we have that just to keep that updated. So the next step is we would set it for 08, but we're not going to go that far because, again, we decided that we would set our clock to 7 to grab stars in the morning. So we're going to do that. Okay, so the alarm is set for 7. When 7 rings, when the alarm clock rings, we will head up and head to the bridge and take sights. Okay, so in the meantime, again, always check the course so you can see we've drifted because of the weather. Let's get back on to 133.
Ruder 0.
Okay, that's close enough. Go. Alright, and let's go ahead and group up. For your sights, it's a good idea to learn a handful of stars. There's like 6 or 7 that I know that I can recognize, and so I use those and just use them over and over again. It's probably beneficial to learn more, but for all intents and purposes, as you're doing this, you find yourself only using 4 or 5 consistently. So, right, so there's that. We'll head up and pick out what we want. Alright. That actually looks a little dark for twilight, but we'll go with it. Alright, so the stars that I'm going to choose are that's what we're looking for is about a 90-degree difference in azimuth. Okay, so you can see off my stern is Shadar right here, and Pollux is here, so it's maybe a little over 90, pretty close, okay? Alright, so let's do that. So we will pull up our E charts here, go to Real Navigation, pull up the list of stars. What we're concerned about at this point is pulling the number of the body that we want to pull. And so we'll pick one first. Let's just pick Shadar first. I'm going to make a note in my notebook here, just off screen. I'm also going to do site reduction using an online calculator because it's easier to see, and I know the Hunter, who I talked to about this video, it's easy to do when you're starting to use the calculator online or alpharensis file. I have not used alpharensis file. I'm not super comfortable in it because I haven't spent time in it, but I've learned site reduction using hand methods and not necessarily that file, and so I'll use what I know, what I'm familiar with here. Okay, so but typically in the run-of-the-mill, you know, doing this, I'll use like historical logarithmic tables, whether that's the FUST nautical tables or the FTOP, which is the which was a site reduction table set specifically designed for the case my unit during the war. Okay, so Shadar and Pollux, that's what I have. Now when I make my sites, I'm going to note a couple things down, but we'll start with Shadar, so that is going to be number 3. So when I grab this and let's just get oriented here, that's going to be off my stern right here. Oops. I plug 3 in. That's okay. Enable. I get back here to where I need to be. Here we are. Line it up just below the body there. And then right about center mass. We're good. Okay. So there we go. Now let's do it again so I can note the exact altitude when I take it. That's okay, 3211.3, I write that down, 32 degrees, 3, and then the time is 5:36:39. Okay, alright, now we do Pollux. Pollux is going to be number 21. Drop 21 in here. Let me go find it. It should be over here. Right there. There's Pollux. Okay. Grab that. Boom. 58:35.1. 58:35.1. And that was at 5:47. 18. Let me measure it again in case that was not right. Alright, let's do it again here. Alright, 58:33.5. And that's going to be at 5:47.48. And then just for good measure, let me do Shadar again because I'm having doubts now about my other measurement. Okay. 32.3. And that's at 5:48.36. Okay, we got the times, we got the altitudes noted down, so we're good. Okay. So now what we're going to do is go down and grab our DR position as of this time, because we're going to need that information as well. I'm also going to note my watch time down right now is 7:05. Good. Okay. as of then, we knew we made this mark here at 04, so that's like 3 hours and 4 minutes, right? So 3 hours is 180 minutes, so 183 minutes we've gone have transpired, so 183 at 8 knots is drop to 0, 180, 3, there is like 44 kilometers. Okay. So we're gonna do, doesn't have to be, okay, there we go. Alright, so that is my DR position as of the observation. Okay, so this is the position we're going to use. For, it's good to note that down so we have it. So again, this is going to be okay. So our DR position as of the observation was, again, rounded to the closest divisible number by 2, so that would be 20 divided by 2 is 10, so that's 5710 north. And then longitude is, again, rounded to 70 because we can divide by 2, so 35, so 4 degrees 35 minutes east. Alright, that's our DR position. We're going to do our calculations based on that. Okay. Alright, so we've got our heights, we've got times, we've got our DR position. Okay. Alright, so the first thing we have to do is we have to figure out what the GHA, what the local hour angle is of our bodies. And so what we want to do is go to the site reduction calculator here. If we're going to use this tool, what we need to figure out is what to input here. So we know our assumed position. We just took that. The longitude was 435, and that was east. And the latitude is 5710, and that is north. Okay, so we've got that in there. Greenwich hour angle. What this is is the Greenwich hour angle of Aries plus the sidereal hour angle of the particular star we're looking at, and so we can figure those out now. So I like using this set of nautical almanacs here. If anybody's looking for this, just ping me or post in the comments. I can send or post a link to it. But at any rate, it's tabulated by the hour, and the figures for Aries are good. You just can't use SHA declination for the sun or for stars with this, because the values in the game are different. But for figuring out like the sun, the GHA of the sun and the GHA of Aries, perfectly fine to use. Okay, so for the third, so let's take Shadar first. Our observation was at 5:48:36, so we go down to the 3rd of November, and we find the hour 5, which is here, and I'm going to just plug all this information into a calculator as I go here. Okay, so we've got 116, and we got 33.4, right? So we can I would suggest just jotting this down. So 116, 33.4. Okay, that's as of the hour. Now the other thing we have to do is we have to figure out for 48 minutes and 36 seconds. So there's a table in here for interpolation, for increments and corrections, right here. So we want to do for 48 minutes. We find the Aries columns here. 48 minutes is going to be, that corresponds to 12 degrees 2 minutes. So we add that, 12 degrees 2 minutes. That's going to give us 128:35.4. Okay, now we need to do 36 seconds. So 36 seconds, we come over to this column, that's 9 minutes. We add 9 minutes. That's going to give us 128:44.4. Okay, that's the GHA of Aries for the exact time of our observation, which was 5:48:36. Okay. We need to do the same thing for our other observation, which was at 5:47:48. So again, 116:33.4 for the amount on the hour of 5 o'clock. Now we interpolate for 47, which is here, 11 degrees, 46.9. Okay, and then we've got, so that gives us 128. Let's see, 13 and 0 is 20. 128, 20.3. Let me just check that. Yep, that's right. Yep, 128, 20.3, and then we have to interpolate for 48 seconds, which is here. 48, that's 12 minutes. So we add 12, so 128, 32.3. Okay. All right, so those are our GHAs of Aries as of those times of our observation. Now we got to pull, we go into the game and we pull the SHA down. This is the sidereal hour angle for these particular bodies. So for Shadar first, we find SHA here. We have to add 350, 41.3. All right, so we do that math. We add that to the number we just figured out, and that is going to be 9, 7. We end up with 479.25.7. We subtract 360 because our answer is over 360, which gives us 119.25.7. 119.25.7. For our first observation, that's what we drop into this calculator here. Okay, 119.25.7. Whoops, what am I doing? 119.25.7. Okay, that is the GHA of Aries as of the second, down to the second of the observation, plus the sidereal hour angle of the particular body we observed. Okay, which changes very, very slightly over the course of time. Okay. All right, so 119.25.7. Got our DR. Now the other thing we need to do is declination. So again, that you pull from the game. That is 56:15.9. The plus means north. 56 degrees, 15.9 minutes. 56 degrees, 15.9 minutes, and that's north. We're east, we're north, north, we're good. Okay, so now we reduce the sight. All right, our computed altitude is 32. We note that down, 1.7. Now we need to do, and the azimuth is 327. Just round it down to the degree. Okay, so 327. All right, so we note those down. Now the other thing, one thing we have to do is we took the sextant altitude right off the face of the sextant here, our reading, but that's not what we need to use. We have to actually adjust that for a combination of adjustments that's in German is called the Gesamtbeschickung, which is actually an easier. It basically means the entire adjustment. It's the culmination of things like the height of eye adjustment, which is called dip, refraction. In the case of the sun, like semi-diameter of the sun, since you're not measuring the middle of the sun, you're measuring the bottom, etc. That table is included in here as dip and refraction table, and then since we're doing stars, we use stars. So we go down to 5 meters. We use height of eye of 5 in SH5, and we find the altitude that we measured, which in the case of Shadar was 32 degrees 3 minutes. So we go down to 32. We find the closest amount, which is here. We subtract 5.6 from our measured altitude, which was 3 minutes, which gives us 31 degrees 57.4. That's our observed height. Okay, that's the one we're going to compare with the calculated height. Our calculated height was that the calculator figured out was, well, we can actually put that here and let it do the work for us. Okay, 31. We could even actually, let me just experiment with this really quickly here. If this is going to work. Otherwise I can input it here, but I could probably put the instrument reading in here, which is 32.3. Okay, and then we'll use the index error as the entire adjustment and see if we can trick it into, since we know what the adjustment is, we don't need to calculate anything. Let's do 5.6. Let's see what that gives us. 32.7.1. I'm not sure what it did. I want my observed altitude to be 3157.4, so let's try something different here. It's still giving me a little difference. 55.8 versus 57.4. Maybe that's not going to work. Yeah, something in the background is doing something. So anyway, let's just see if we can input it directly in here. 3157.4. There we go. Whoa. Interesting. Yeah, I'm not sure what this is doing. Well, at any rate, it's doing something in the background. That's some automatic calculation that we don't want to worry about. And so what we want to do is compare 3157.4 with 32.1.7. The difference between those is going to be our intercept. Okay, the intercept is going to be, oh, hold on, actually, let me see if I can do this, and then just do, let's just put the adjusted amount up here, 3157.4. Is that going to just take me? No, it's still not going to do it. 3155.8. Yeah, weird. If I put height of IF5 in there, let's see if it does anything. Or 32, 1.7. Oops, 32.3, excuse me. Okay, that's close enough. 3157.5. Again, we used 5.6. You could always just pull the computed altitude and then use the adjusted observed altitude that you figured out, but this allows us to actually see it. Okay, so the azimuth is 327. The intercept is 4.2 nautical miles away. Okay, because the observed altitude is lower than the computed altitude. What that means is, because the angle is lower, we are farther away from the body than we thought we were, which makes sense if you think about it like in your periscope, right? Like if you're measuring range using your scope, the angle that you measure, if it's higher, that means the target is closer. If it's lower, the target appears smaller, it's further away. It's the same concept here. If the observed altitude is lower than the computed, means you're further away from the body than you think you were, which means you need to plot away from the intercept, okay, or from the azimuth, basically on the reciprocal of the azimuth. So in this case, it's 4.2. Again, since lat long is 120 kilometers, we need to multiply that by 2. So that's going to give us an intercept of in kilometers to use of 8.4 minus 8.4. Okay. All right. So we've got the first site. We'll do the same thing for the second site. The GHA of Aries for the exact time we computed was 128.32.3. We need to add the SHA of Pollux, which is going to be here, 244, 32.5. So 128.32.3 plus 244.32.5 is 373.4.8. Let's make sure that's right. 13.7. Alright, which is more than 360, so we subtract 360. That gives us 13 degrees, 4.8 minutes. That's what we plunk into the calculator, right? So we go here and we say 13, 4.8. Okay, now we need the declination because we've got a different amount for, we got a different star now we need to worry about. So that's north 28.8.7. Okay, that's good. Height of eye is still, we put our observed altitude in, which was 58, 33.5. And I'm going to just adjust that actually using the hand way, using the table. Let's look at that. 5 for 58, 33.5 is about 4.6. So that should give me, if I have to subtract that from my measured height, which is going to give me 58 degrees, 28.9. Let's just check that against what this does here. 58, 33.5, 58, 29. That's pretty close. Okay. All right. Okay. So then the computed altitude is, let me just double check everything. 4.8 and declination 28.7. $28.8.7, 244, 32.5. Okay, all right. So then that's giving me an azimuth of 211 degrees. Just round up, 211, and intercept of 3.9 towards. And it's towards because I measured or observed an altitude higher, an angular altitude higher than the computed altitude. That means I'm closer than I assumed, than my assumed position was. If I were actually sitting at this position, this would be 0. These would be equal. But since we're not sitting on at that position, we're actually 3.9 nautical miles closer to the body than we thought we were. So we plot toward 3.9 times 2 is 7.8. So I say plus 7.8. All right. So we've got two azimuths, and we've got two intercept numbers. Now we're going to put those on the map. Now what I do is I do it off to the side someplace. Well, actually, since we're using DR position, let's just do it right on the DR. It's easiest. Okay. So right here. So our first azimuth was 327 degrees, so we draw that. But because it's away, we need to draw it down the other side because we're actually going to plot it away from 327. Make sure we're good. We're going to plot it away from 327. It's not going to be quite 3. It's going to be actually away. Okay. Oops. Matter of fact, let's just do 327 minus 180 is 147. 327 147 minus 180 is 147. So then we'll just plot it at 147. Okay, easiest. Go. 147. Okay, right there. And I know it was 8.4 kilometers. So I measure that. Say 8.4. Okay, now I've got the azimuth and I've got the intercept, which is this distance here. I need to draw a perpendicular to that, and that is going to be my line of position. That is right here is my line of position. Okay, I am anywhere on this line here. It's really a small, tiny part of a huge circle that goes around a part of the Earth. All right, and that circle is equal to the nautical miles. If you were to take 90 minus your sextant altitude, that amount is called the zenith distance. That if you compute that in minutes, arc minutes, an arc minute is a nautical mile. That would be a giant circle of a radius of that zenith distance amount in nautical miles. But since that circle is so enormous, we represent it as a straight line when we're doing this. Okay, so that right there, anywhere on this line here, if you were to extend this line, that's where we would be. Okay, so not enough information, right? We need a second. We need a second one, so we're going to get that, and that's what the second star provides. So the second azimuth was 211, and that was toward. So we're going to do 211 like this, and then we're going to adjust our distance to be the intercept of 7.8. Oops. 7.8 right there, and then we draw a perpendicular to that as well. 90 right there. Okay, that would be our fix. All right, if we were on if we were plotting this on a Mercator chart, but we're not. We're plotting it on a flat, essentially a flat piece of paper, because that's what the world is in SH5. So in order to fix that, what we need to do is we need to figure out what Alfred's calls the spherical transfer, which basically is taking you're adjusting your longitude by the secant of your latitude. Okay, so we're going to do that now. So what we do is we draw a vertical line like this, and then we measure the angle from that line to our fix right here, and then we say our closest line of latitude is 57, so we set that to 57. Okay, like that, right? It's not super exact, but that's okay. And then we adjust that distance. We adjust our fix over by that distance, by the distance of the hypotenuse right here. We then put that over here. Oops, and we say, all right, really we're not here, we're actually here. All right, so like that. So our fix, latitude is fine, right? There's no issue there. It's longitude is the issue because all the longitude lines are parallel. We need to adjust for that, to fix that, and we do that by way of this so-called spherical transfer. Okay, so that was here. We've now moved it over here. This is really where our fix is right here. Okay, so we can get rid of everything else. So there we go. We thought we were here. We're actually really here. The amount we were off by was like 5 nautical miles. Okay, which is fine because we've had horrendous weather with our speed fluctuating all over the place, and our DR has not been super exact. So that makes sense. Okay. All right. So from that point on, we can say, okay, start our DR from our new fixed position here, and we get a new course down to Helgoland, which is here. So we're going to be back on a course of 132. We've drifted significantly here. Let's get back to 132.
Ruder 5 Grad Backbord. Neuer Kurs 131 Grad.
Okay, so then what I do is I just make a circle around that to show that that is my that's a fix, and then we are good there. Okay, so that's our new fix. So then what I want to do is, since I made a note here, a placeholder note, let's get rid of all this here. I want to update this with the actual position, which is going to be which we can measure. So let's measure that now. So that is round that up to 10, divided by 2 is 5. So our and then let's do our longitude. Okay, so we've got enough information here. So we do 57.5. So this is fix 57.05 north, and 4, and then we can round it down to 72 because it's divisible by 2, and that would be 36. So that's 436 east. Right, and that looks about right. Right, so that's our fix. There we go. Okay. Alright, so that's the star site in a nutshell, using the online calculator, which is much easier than doing it, well, at first anyway, much easier than doing it by hand. So, that being said, that's the first site of the day, okay? Now, the next step is to figure out when local area noon is going to happen. So, there are a couple ways to figure this out. The easiest way to do it is to do that nautical almanac that I showed before has a table at the bottom that shows when the sun will pass Greenwich, the meridian at Greenwich, the prime meridian. We want to get to November 3rd. Here we go, right here. On November 3rd, meridian passage at Greenwich will be at 11:43. Why is it not noon? It's not noon because of something called the equation of time. The Germans called it back in the day the mean sun versus the true sun. So the true sun is the actual movement of the sun around the Earth, which forms an ellipse, whereas the mean sun is sort of the perfect scenario of the sun traveling around the Earth, if you want to think of it that way, not in an ellipse. The difference between that elliptical movement and the assumed average mean movement is what's called the equation of time. So it's not noon at GMT. It's 11:43 GMT is when the sun will pass 180 degrees south, basically on the meridian line of, if you're standing in Greenwich, England. Okay, so we use this as a starting point. We say, okay, 11:43, 11. We can write this down. We can say 11:43, and we do the same thing that we did when we figured out twilight. We say, okay, at this time, whereabouts are we going to be, and what longitude are we going to be at that time, and we're going to subtract that east longitude. If it were west, you would add the west longitude, but since we're east, we're going to subtract that because the sun is going to get to us before it gets to Greenwich. Okay, so 11:43. So then we say, okay, where do we think we're going to be at that time? Roughly, it doesn't need to be exact. So we're here. We took that site at 7:05. Okay, because it's zone time, we need to add an hour, so that's really 12:43. 12:43. And then we subtract, so that is about like an hour, a little over an hour and a half. What did I say? 12:43. So that's like 5 hours and 5 hours and 40 minutes. So 5 hours is 300 minutes plus 40 is 340. 340 minutes. We then figure that out based on we figure out how far we will have gone by then. 340 minutes is, we drop the 0. That's about just under 8, so like maybe 79. Maybe 79. So we move 79. All we're trying to get is an approximate longitude that we'll be at local noon. So that's going to be like 5.2, maybe 5.1, 5.2. So 5.2 degrees east. So again, we do the math. We say 5.2 divided by 360 times 24 gives us 0.34 hours times 60. That's 21 minutes. So we subtract from our 12:43. We subtract 21 minutes. We know local time, so the time on our clock, it's going to be 12:22 is when local noon is going to hit. We don't want to be up there at the time because we don't want to miss it. So what we would do is we would go up there maybe about 5 to 10 minutes before that, so we can measure the altitude of the sun. Okay. All we're doing now, though, is noting that time down for the future, because what we're going to do is we're going to take a sun site before that, and we're going to advance it up to that particular point. All right. So, because I make a notation every 4 hours, let's bump this up to 08. Go ahead and TC up. I want to go 32.
Ruder 5 Grad Backbord.
32.
Ruder 0.
Alright, that's good. So then we can say, let's keep moving. So at 08, we will have gone 55 minutes. So that's like 12 kilometers. So I go 12 kilometers. Alright, so that's my spot, that's my position as of 08, my DR. Okay, and then I want to make a note what that is. That's going to be about 57.1, and oops, and then I want to make an entry. That's going to be oops. Not sure what happened there. There we go. 57.01 north, and for that's 82 is divisible by 2, so that is 41 east. Okay. All right, that's my position at 08. I've already got my weather report as of 08, which is good. All right, there we go. Weather's still atrocious. Alright, so that is good. So now I could say, okay, the next one's at 12. Well, that's not the case, because I want to take a site. And I want to take a site about 2 to 3 hours before the time that I calculated for local area noon, which is 12:22. So I want to say, let's say at 10. go up and take a sun site at 10. Alright? Alright, so we'll do that.
Laufen auf beiden Dieselmaschinen.
So we'll TC up to 10. Here's 10. Let's head topside and we'll grab a site if the weather is going to allow us to. Again, the sun's pretty low. I wouldn't typically rely on sun sites with the sun this low, but just for the sake of demonstration, I'll show how to do a running fix in the sun. Okay. Alright, so we do the sun, we know is 0.
Ruder 0.
Use the keypad for these numbers, by the way. And we find the sun. And it's a little foggy, so this is going to be super exact, plus the altitude is really low. We'll just show for demonstration purposes. Take a shot here. It's very hard to see the lower limb of the sun here given the fog, but we'll take a best stab at it again. I'm not expecting this to be exact, to be accurate at all. Let's just call that good right there. Down 11, 5.8, 5.8, 11 degrees, 5.8, and the time is 8, 44, 43. Okay, so we've got those numbers down. Alright, that's good. We will go ahead and reduce the site. No, we're not going to plot it yet. Excuse me. We're not going to plot it yet. We're going to plot it when we're at the second location. For now, we're just going to reduce the site. So, 11 degrees, 5.8 minutes was our altitude, 8, 44, 43 was the time. Alright, so again, we go out. Now I need to use GHA of the sun, which is here. So we go to 0800, and we jot down 304. 5.5 on the hour. Now I need to interpolate for 44 minutes right here. Oh, using the sun increments. So that's 11 degrees. And then for 43 seconds, that is 10.8 minutes. Okay, so that is 315, 16.3. That is the GHA that we need to put in. There's no SHA. We're just doing the sun right now, so it's just GHA of the sun to the second. Okay, which is 315, 16.3. So we drop that into our calculator here. 315, 16.3. Okay, that's good. Now the declination of the sun that we need to get from in the game. So that is going to be from Alpharensis tables here, which is going to be. Oh, he might not actually have the declination of the sun in here. That might be actually elsewhere in his charts, which I can pull up. So okay, so he's got that in here. He's got that. This is his real navigation documentation folder. He's got that in his nautical almanac here. Okay, so we can look at that here. So the first section is for Aries. The second section is for the sun. It's going to load here. Here we go. August, September. We're looking for November 3rd. Okay, 1939. Here's declination right here. The time was 8:44. We're gonna use a ballpark figure. We don't need to do it exact. Let's just call it so south 1439. 1439. Okay, so that's our declination of the sun. They're different than those in this file here for the sun and for the stars. Okay, so all right, so we're at 1439, and that was south. So we changed that to south. Now we need to figure out where we are, where we think we are. Okay, so the time of the observation was 10 o'clock. The last DR position we took was 8 o'clock. Okay, so that's 2 hours. So in 2 hours at 8 knots, 2 hours is 120 minutes. Drop the 0, go 12. That's going to be like 29 kilometers. Okay. There we go. Okay, so that's where we think we are. Now we are going to jot the lat long down of that roughly, which is going to be 56 degrees, and this is divisible. 102 is divisible by 2. That's 51. So 56 degrees, 51 minutes north, and 4 degrees. Let's bump this up to 104 so we can divide by 2, which is going to be 52, 4 degrees, 52 minutes east. That's what we plunk into the calculator. 4 degrees, and I said 52 east, and then 56, 51. Okay. This we put in, that we put in. We're good on these. Now we do. Now the we're not going to worry about doing all this stuff for the stars for the sun because of all the different adjustments for it. We're just going to use the total adjustment, so we can compute 11, 12.4. The altitude we measured before was 11 degrees, 5.8 with the sextant. We need to adjust that. Now, the adjustment that you're going to get here is going to be a little wonky because of the fact that the sun is so low. But just bear with me because it's not going to be a perfect exercise by any means because the sun is so low. It's just for demonstration purposes. So 11, 58. We're going to always add this adjustment because the net effect of it is a plus because we're measuring from the bottom of the sun. And we need to adjust to the middle of the sun. 11, 5.8, so let's say 11 degrees, so that positive adjustment is going to be 7.3, right? 7.3. So we say plus 7.3. We add that to our sextant altitude, which is going to be gives us 13.1. And then what will the calculator give us? So let's just do 13.1. So you can see now we're comparing the two. Our observed height is greater than the computed. That means we're closer to the body than we thought we were by 0.7. The difference between these two here is 0.7, and that's positive. Okay, because observed is higher than computed. We're closer than we thought we were, so we have to go toward the body along this azimuth, which is 141 degrees, which we also note down. Okay, so plus 0.7, 141 degrees. That's the data we take from this. Okay. All right. So pretty small intercept, which is good. All right, so that's the morning sun sight. It's the morning sun site right there. Okay. So we'll just keep this as is, and then we're gonna look back to our local area noon amount that we figured out from before, which is 1222. And we're gonna do 12 instead of 22. We're gonna go 1, 2, 3, 4, 5 back from that 1217, just so we know we can catch it. And we'll actually do a measurement and we'll shoot the azimuth of the sun too, just to make sure we know when it's. We can see when it's 180 degrees. Because when the azimuth is 180 degrees, when the bearing of the sun is 180 degrees true, that's local area noon. It's crossing your meridian. Okay. All right. So 1217. We're good. We're gonna have to adjust our course back down to
Ruder 5 Grad Backbord.
132. Oopsies.
Ruder 0.
There we go. Alright. That's good. Okay. Alright, so we'll go ahead and TC. Alright. As soon as the bell rings, we'll head up. We'll head topside and start measuring the altitude of the sun. Because what we're interested at that point in time is figuring out when the sun peaks, when it reaches its maximum altitude, and then starts descending again. That maximum altitude, we'll do a little math and we'll figure out our latitude from that. Okay, alright, so here we are. This puts us about 5 minutes or so before local noon. And we'll shoot, first and foremost, what we'll do is we'll shoot an azimuth of the sun. Okay? So we'll use the attack disc for this. Slave it to course. Set the pointer to 180 degrees. Right here. Hold it right there. That's true. Read off the relative bearing. We need to look. And that is about 48 and 49 degrees relative. Okay. Alright. So find the sun. So you can see it's about 45. Once it gets to about here, that's going to be local noon. Again, we're yawing all over the place. So 48, 49. So the sun is there. Once it gets to 48, 49, we know we're at getting close. But just let's start taking sights here. We can start jotting altitudes down.
Ja, bitte?
Oops.
Ruder 0.
Clouds kind of help a little bit define the sun for you, because otherwise it's hard to tell where the edges are. Alright, so right about there. Alright, 8:21, just round it down. 18:21, excuse me. 18:21 is our first altitude. We just jot it down. We don't need to worry about the time or anything. We don't care about time at this point. We're just trying to determine is when the sun reaches maximum altitude. So we wait. We wait a little bit. Okay. Right. Make sure we're at 32, and then we can just shoot another bearing of the sun here, make sure. Okay, yeah, so we need TC a little bit here. Just TC a little bit, just to speed things up. There we go. We'll take another azimuth, or take another altitude here.
Ruder 0.
I don't want to do that. 1824, so it's risen a little bit. Note down that 1824. Just trying to determine when it's at its highest point. All the while we do that, we'll still kind of take bearings of the sun, make sure it's, once it gets to about 48, 49 degrees there relative, we know that's going to be at correspond to 108 degrees true, which is our meridian.
Ruder 0.
Maybe 25.
Ruder 5 Grad Backbord. Ruder 0.
Okay. Yeah, so it's getting there. Closer. Did you see that? Take another one and take advantage of this cloud coming there
Ruder
to shoot
0.
the sun for us. Or completely blot it out. Come on here. Wait. Alright. 27. 1827. So it's rising, which is good. Alright, getting down. Let's just take another, make sure we're set. Okay. 80. Relative bearing should be 80 should be 48. Okay. 48. Alright, it's getting a little closer. Can you see a little more? Reading.
Ruder 0. Maybe 28. Okay. Ruder 5 Grad Backbord. Ruder 0.
Yeah, the weather really messes with your
Ruder 5
With your
Grad
steering.
Steuerbord. Ruder 5 Grad Steuerbord. Ruder 0.
Alright. What are we doing here? Get a little closer. Gonna have time. It's 22. Oh, okay, so it was actually a little later. Might be right about now.
Ruder 0.
decreasing,
Ruder,
and then
0.
we have all we need. Alright, well, it's about 29 now, so I'll go 29. 1829.
Laufen auf beiden Dieselmaschinen. Ja. Ruder 5 Grad Backbord. Ruder 0. Laufen auf beiden Dieselmaschinen. Fahrt bei dem Wetter 1. Ruder 0.
Alright.
Ruder 0.
Should see it start decreasing now. It drives me nuts when it zooms out like that. It's a bug. It has to do with the UZO.
Ruder 0.
So we see an altitude lower than 1829. We know we're good. Just take the approximate time that happened. Just right there. Alright, so let's actually call it 1830. Let's take an azimuth. Should be. Yeah. Okay. 1830 is going to be peak, so we'll call it good at 1830. All right. So 1830 was our maximum height that we observed. 18 degrees, 30 minutes. Do just that. 5 meters, 18. So 9.3. Plus 9.3, which is 18, 39.3. So the calculation for latitude and local noon is a little different. It's much simpler. So what we do is we take the zenith distance, which is 89, 60, so 90 degrees, which is, you can convert that to 89 degrees, 60 minutes for ease of subtraction, minus the altitude, which is 39.3. That answer is 71 degrees, 20.7. That's the zenith distance. Okay. Now, the only other piece of information I need to consider is the declination. Now, what do I do with the declination? Well, whether you add it or subtract it will be different in different situations, but the easiest thing to do is just to say, what do I need to do to my that zenith distance angle to get to my latitude? Well, I'm at 71 degrees, 20.7 minutes. I need to subtract something to get to my latitude, because I know my latitude is about like 57-ish degrees. Okay, so clearly I need to subtract something. That something is the declination. So we go and we pull that amount again, which was here, which I think we said was 14 degrees 39. No, excuse me, we need to figure it out again because we're at a new time now. So the time was about like 11:30, 11:40, somewhere in there. So it's going to be, the declination is going to be about 1441. So we subtract 1441 from our zenith distance that we already figured out, and that is going to be 56 degrees 56 degrees and 40, about 56 degrees and 40 minutes. 56 degrees and 40 minutes. .56 and 40 minutes is what our longitude, or excuse me, latitude should be. So that's our latitude line, 56 degrees 40 minutes. All right, so all I did there was I simply took 90 minus my sextant altitude after adjusting that sextant altitude for the adjustment here, right? The total adjustment. I took 90 minus that number, zenith distance. Then I take the declination, which you have to get from his tables here, the nautical almanac. And I said, what do I need to do to these two numbers to get them to be about what I think my latitude is? Well, I have to obviously subtract one from the other. So subtract the declination from the zenith distance with 71 degrees minus the 1441 declination that I pulled from here, got me to a latitude of 56 degrees and 40 minutes. So 56 degrees and 40 minutes. So I need to figure out where I think I am at this time. So we took this site here at 10 o'clock. It is now, when I did the site, it was probably 12:40. So that's 2 hours and 40 minutes. That would be 2 hours and 40 minutes, which is 160 minutes. So I say drop the 0. That's like 30. It's like 38 kilometers. Which is there. Okay, so that's where I think I am, right here. That's where I think I am. From this spot, I'm going to plot both the 10 o'clock sun line and the latitude line that I just figured out. Right? So, there's nothing to plot for the latitude line. We just draw the latitude line in. So we'll do that now. So we think our latitude is 5640. So we'll say from 56. Remember, we have to double the 40 because everything is double on the map. So 5680, which is here, close enough. Okay, right there. That's our latitude line there. Alright. So that's the latitude we just took. That's the noon site. Noon site for latitude is just a simple site. You get the maximum altitude of the sun. You make some adjustments to it, do something with your latitude or with your declination to figure out what your latitude is. Okay, simple. So the other site we have to plot because we took it at 10 o'clock. And so the numbers we figured out for that were plus 0.7 at 141 degree azimuth. Okay, so 141 degrees. Draw that. 141 degrees right there. Okay, and then 0.7, which we double to be 1.4 kilometers. 1.4, which is just going to be here. now we draw a perpendicular. And where that, here's 90, where that crosses our latitude line is our running fix. A running fix. So what we did was we took that site at 10, and we effectively DR'd, dead reckoned that site up to our position as of local noon, which was here, and then we took the local noon site, and then where those cross is our running fix. It's not perfect, but it's what you do during the day, because you only have one body usually. As long as the moon isn't visible during the day, you typically only have one body during the day to observe, and that's the sun. So we do running fix, and so right there is where that would be. And so we need to do our transfer. Oops. We use the one we already drew, which is here. We need to do our transfer for our longitude based on our latitude. Here's our fix right here. Now, the other thing I will say is that this I know is too far north because the sun is so low. It's because of the distortion of the sun disk and the disk of the sun in the game. What you're measuring is not necessarily the true, and the measurements you take and the adjustments you make to those measurements are not necessarily getting you to the accurate center of the sun. So I know that's going to be a little off. Okay, but that's okay because we're close, and this is really just meant to be an approximate fix anyway. Okay, so here are our lines of position. There's the latitude line. There's the line of position from 10 o'clock in the morning. So now we want to do the transfer. We simply just take this and bump it up to 50. So 57 is the closest. Okay, and then we do like this. We extend that up so that the radius is up to up here, and then we move that over, and we transfer that over here. That is where our position is, we estimate, from our running fix. Okay? Right. So that we think we thought we were about 5 nautical miles away from where we actually were. Alright? And again, I think this is not quite accurate because I think we're a little too far north. Okay? Alright. So that's good. So that's our running fix. That's our running fix. And that's the last sight I do during the day. If I can't get that running fix, I'll take another star sight at night. But since we got both fixes during the day, that's pretty much, I'll pretty much call that good for like the celestial day here. So what I would do from here on out, so again, I would reset my DR from this position. I do think we're actually a little more in line with our course line, but we'll just pretend like that's an accurate fix. And we would say, okay, we want to still steer toward Helgoland. So that is, our new course would be, well, we'd steer about 133. Okay, 133. So we have to adjust our course back to 133. And then I'm going to update the log. Oh, you know what I forgot to do is I forgot to make a note right on the time. But that's okay. We're just going to get some cleanup here. And then we're going to do, there we go. And then we'll make a new entry actually cancel. And then we're going to figure out what our fixed position is. So we'll say it is 56 degrees. Hold on. Let's get everything drawn here. Alright, so 80 is 40, so 56. This is our fix now, running fix. 56, 40 north, and 5. 20, half of 22 is 11. 5, 11 east. Okay, that's our running fix. Running fix. There we go. Okay, was a little before. It wasn't. It was a little before 12:53, but that's okay. So let me edit that to say at 12. It was at about 12:35. Our fix 56, 40 north, and 5:11 east. Okay, there we go. That way we just correct the time in there. Okay, so that is that. We will, from here on out, what I would do is I would simply DR. So I got my 2 celestial fixes for the day. I think I'm probably good. I would at this point just DR every 4 hours. I would figure out what my 12 o'clock position was by just going back a half hour. I won't do that, but just basically take my 12:35 position and just DR it back a little bit to 12, and then make my every 4 hour notation, so right on that 12 o'clock. Because technically what you would do, a celestial day goes from noon to noon, and you would compute your day's run from noon to noon every day. In German that's called an Etmal, ETMAL, and you would, if you look at the historical logbooks, the KTBs, you would have every noon during the day, you would have a notation for the day's run, how many nautical miles were traveled surface, how many nautical miles were traveled submerged, and that would be effectively your day's run, which is how you basically compute your kind of overall speed over ground, if you will. But so that's why it's important to have a figure at 12. So you go back and figure what your time was at 12 o'clock, or what your position was at 12, and then 16, 20, 24, 4, 8, etc., right? A DR every 4 hours, right? So that's what the rest of my day would look like in here as I work my way down here. So I won't go any further than that. That's what I typically do. More of a truncated version than what would be done in real life. However, I mean, I've seen plenty of KTBs where it only looks like the navigator is doing 2 fixes a day. Like even if you look at U-96's 7th Patrol, the navigator would have done typically a morning sight, which would have been stars and planets, and then he would have done what looks to be a noon sight, which would have been combined with another probably another morning fix to get a running fix, which is what we did, in order to get a fix during the day, and then he'd forego the evening sight in a lot of cases. And if he couldn't get that noon sight or whatever, some sight during the day, he would then take an evening sight, or if there was a particular reason why they needed to know their position as of the evening, as an update, maybe then. But by default, I would say, a good rule of thumb is to just get 2 fixes during the day, whether that's 2 star sights, whether that's a star sight, whether that's a morning sight and a running fix during the day, or a running fix during the day and an evening sight, whatever. But two fixes is probably sufficient for this purposes in the game. So with that, that's pretty much it. I'll end it here. I know I didn't demonstrate a lot of the calculations. I did them sort of off screen. If anybody has any specific questions about what I did, please let me know. But we went over the calculation of nautical twilight. We went over how to pull, how to do a star site. We went over how to compute GHA and how to get sidereal hour angle, so GHA to the second plus SHA to put it in here, and then how to pull the declination, and then we put our assumed position in here, and then we let this website do the math, and then we figured out the intercept based on comparing the adjusted sextant height that we took and then adjusted for, compared with what was computed by the calculator here, and then got the azimuth that was computed by the calculator, and then we did the plotting directly on the map in SH5. So that's pretty much it, I think, for the video. Again, like I said, let me know if anybody has any questions about anything, but really this is just to show kind of what a day would look like. So, alright, thanks, take care.